All right. So what I was saying is that I'm going to discuss some of the interesting tools that is I find quite useful when it comes to understanding wave dark matter halos and their interaction. So again, the wave dark matter is kind of very vague term. It can mean basically anything. So let me start by defining what I mean by wave dark matter. So in this talk, I will use a wave dark matter and ultralight dark matter as interchangeable terms. What I mean by ultralight dark matter or wave dark matter is any light bosonic dark matter whose mass is smaller than 10 eV scale. So what is so special about this ultralight dark matter is that whenever your mass goes smaller than 10 eV scale, now what you are going to see is that within the one wavelength of the dark matter, you start to see more than two particles. So we can easily calculate the occupation number or number of particles within the wavelengths of dark matter, and it is proportional to 1/m⁴. So you can easily see that whenever the mass becomes smaller than 10 eV scale, this number becomes gigantic numbers. And this is exactly the property which allow us to describe this kind of wave dark matter as a collection of classical waves rather than individual particles. Hence the name wave dark matter. Again, there are many theoretical possibilities. The wave dark matter is also named. There are many theoretical possibilities that falls into the category of the wave dark matter. So for the sake of the discussion, let me just think about very pessimistic scenario or minimalistic scenario where the wave dark matter only participate in the gravitational interaction. So in this case, there is a single parameter that describes this theory. So there's an Einstein-Hilbert action, there's a kinetic term, and there's a mass term. And this mass term is a single parameter that describes this theory of wave dark matter. And even in this minimalist case, there is actually a landscape of possibility. There's only a single parameter, but the possibility for the wave dark matter is vast in a sense that the allowed range of the mass of this wave dark matter ranges from 10⁻21 eV scale all the way up to 10 eV scale. So above 10 eV scale, this is not wave dark matter in our definition. Below 10⁻21 eV scale, they may not be 100% dark matter in the present universe because of cosmological and astrophysical observation. And what is even more is that almost all range of this mass is practically allowed, except for very small narrow range of the this landscape. And also what is even more is that once we start to include their, well, here I'm kind of vague about this mass scale. So of course there are many astrophysical constraints. Some of them claims to be constraining 10⁻20 eV scale. Some of them claims to constrain 10⁻19 eV scale. So here I'm not claiming that 10⁻21 eV scale is allowed, but just more as just rough numbers of the lower end of the wave dark matter. So it's not to say that this is completely consistent to the cosmological or astrophysical observation. Yeah. And what is even more is that once we start to allow their coupling to the standard model, then this one-dimensional landscape becomes n-dimensional parameter space, and there are much more possibilities, basically posing challenges for the wave dark matter search. But we can look at this situation in a different angle. The fact that it can couple to standard model non-gravitationally, and the fact that there is a still wide range of mass range, which is allowed observationally, will allow us to have more handles to search for ultralight dark matter. For instance, if they happens to have some interaction, the non-gravitational interaction to the standard model, we can just try to use clever quantum sensor to look for this kind of ultralight dark matter search. So the available coupling of this ultralight dark matter depends really on the underlying theoretical concept or ideas. So in the case of axion or axion-like particle, there could be anomalous coupling to gauge boson like photons. There could also be the axial vector coupling to the fermions. And for the case of QCD axion, they can couple to electric dipole moments of the nucleon field. And depending on which coupling we are looking at, there are a variety of channels that we can look for, a variety of methods that we can use in order to search for a wave dark matter, in this case, axion-like particle. So there is a famous microwave cavity. There is also abracadabra and all the other astrophysical observation that is partially constraining this parameter space where the x-axis is the mass, y-axis is coupling constant to the photon. If we look at the other couplings, for instance, couplings to nucleon field, we see that there's also a lot of different ways to search for axion-like particle. There are cool magnetometers, there are NMR experiment, which is a Casper, and there are other kinds of experiment going on in order to prove a axion coupling to a nucleon field. And if we look at this EDM coupling, now we can look for oscillating neutron EDM, because in the presence of axion dark matter, this neutron EDM will oscillate. So by looking at the harmonic signal and the neutron electric dipole moments, we can search for ultralight dark matter or axion-like particle dark matters like this way. And moreover, if they couple to GG dual, they actually induce a quadratic coupling to pion mass and also the nucleon mass, as well as G factor, the nucleon G factor. And once we have these kind of quadratic coupling, what you can do is that you can use a spectroscopic measurement, such as atomic clocks, or interferometric measurement, such as typical gravitational wave interferometers, to search for similar parameter space where this is a coupling to gluon field in the center matter. So this is one example for the axion or axion-like particle. There are other examples, other realizations of wave dark matter, which is a dark photon, where they couple to center matter through the kinetic mixing. And there are scalar dark matter, which can couple to field strengths of electromagnetism or mass of electrons and other particles directly, such that we can again use atomic clocks or other spectroscopic measurement to prove these kind of wave dark matter candidates. So these are more or less summary of the current status, current efforts in terms of wave dark matter search based on their non-gravitational interaction to the center matter. And so now what I want to do is that I want to switch gear a little bit and discuss something else, something that is less discussed in this workshop, which is behavior of this wave dark matter on the galactic scale or subgalactic scale, purely based on gravitational interaction. So for the rest of the talk will be only about ultralight dark matter with the gravitational interaction. So in recent 10 years, there has been interesting numerical simulations of wave dark matter. So this is numerical simulations of ultralight dark matter, especially when their mass is 10 to minus 22 eV scale or 10 to minus 23 eV scale. And on the larger scale, this is a wave dark matter, this is a cold dark matter. On the larger scale, you see they are more or less same, but there are a little bit smaller number of smaller structure in the wave dark matter halos. And if we look at closely in one galaxy, for instance, if we look at this part, we can also see interesting patterns in the density profile. So unlike the CDM case, there is a characteristic chord profile, which is nothing but the solitons. Soliton is a ground state solution of Schrödinger-Poisson equations, and Schrödinger-Poisson equation is nothing but the non-relativistic version of wave equation. So this soliton, the core soliton profile is nothing but the eigenstate of this Schrödinger-Poisson equations. And outside of this solitonic core, there are some smooth profile, which looks more or less similar to the profile of cold dark matter, something very similar to NFW profile. But this is a kind of average picture. The way that they obtain this picture density profile is by taking average over a certain time scale. So this really should be understood as average density. If we actually look at the simulation, their time evolution, there are much more structure going on. So if you look at the center, you see that there are bright solitonic cores. And outside of the solitonic cores, you see there are bright spot and dark spot. They are repeating in the random manners. So this color code here is density the density of the dark matter. So dark spot means that there is a less density. The bright spot means that there are more density. So there are order one density fluctuation just going over all of the galaxy. And this is not the only simulation that see this kind of behavior. There is other subsequent simulations that has observed similar features. So in this simulation, you see that there are solitonic cores, and outside of the solitonic cores, there are order one fluctuation that is just going over in the whole galaxy. You see also the same feature here, where there's a central solitonic cores, and outside of the solitonic cores, there is order one density fluctuation. So the question is, this kind of order one density fluctuation is another characteristic feature of wave dark matter, ultralight dark matter. And there are several interesting phenomenology associated with this density fluctuation. So now what I want to do is I want to discuss a simple intuitive way to understand this kind of density fluctuation. So one of the simple way to understand this kind of density fluctuation is to think of them as some sort of particles, like a quasi-particle. So their size is given by the wavelengths of dark matter, which is the 1/mv, and their total mass is given by the total mass enclosed within the volume of this wavelength. So this is how I want to understand this kind of density fluctuations. And you can see that the mass and the size of this object depends very much on the mass of dark matter itself. So this is proportional to 1/m. This guy will be proportional to 1/m to the cube. So depending on the mass, their scale will change dramatically. So here, I am showing the typical size and the mass of this quasi-particle as a function of the mass. So if we look at ultralight dark matter, fuzzy dark matter, the quasi-particle mass could be 1,000 solar mass or 10,000 solar mass, whereas the size of this object can easily be 100 parsec or kiloparsec scale. So this is a big, puffy, giant object that is just moving in the galaxy. We can go even higher mass. If we think about 10⁻16 eV scale, the size of this object becomes more like a solar system size. They are 10 AU scale, and their mass could be 10 to 17 kilograms, which is the mass of some of the heaviest asteroid in the solar system. And if we go even further, if we go to say 10⁻11 eV scale, that the mass becomes 1,000 kilograms, whereas the scale, the size becomes 1,000 kilometers. So the 1,000 kilograms is roughly the mass of elephants. So these are elephant size in terms of mass. They are just floating in the solar system. Yeah. Yeah, so here I am choosing velocity equal to 200 kilometers per second, just for the sake of estimation. Of course, if you think about other kinds of structures or dwarf galaxy or galaxy cluster, the velocity will changes so that typical size of this quasi-particle will also changes depending on the system that you are considering. Yep. Yeah, so the virial velocity, just roughly speaking, 200 kilometers per second for Milky Way size galaxy, right? 240, 160, depending on what you like. Yeah, exactly. So we are talking about, for now, say Milky Way size dark matter halo. So the virial velocity of this Milky Way size halo will be, roughly speaking, 200 kilometers per second. If you go to the smaller galaxy, dwarf galaxies, it can be smaller, 10 kilometers per second. If you go to higher, a more massive structure, it can be larger than that. So here, the reason I choose 100 kilometers per second, roughly, more or less, is, just for the sake of discussion. Yeah. Yeah, so all of these, the size of the quasi-particle, all of these things are more or less smaller than the size of the galaxy, because even though you are around here, they are 100 parsec scale. So if you think about really Milky Way size dark matter halo, they are still smaller than the size of the galaxy itself. Yeah. So the Poynting distribution of these particles in the So can you say that again? Sorry, yeah.
What is the distribution of these quasi-particles in the full galaxy?
So what is distribution? Yeah, so sorry, I mean, yeah. So here we are just, I mean, at the moment here, we are just not talking about the distribution, but we're gonna discuss statistical property of these quasi-particles. And then there, maybe it's becoming more clear. So, but in order to naively answer to your question, again, I mean, regarding his question, the size and the mass of this object is generally depends on the velocity and also the density of the dark matter halo. So if you go to the center of dark matter halo, the density will increase so that it becomes more massive. So it may change a little bit the structure or the shape, morphological shape of quasi-particle. But here at the level of this discussion, I'm ignoring those order one numerical factor. Yeah, but that's a very good question. So yeah, so in terms of mean density, you're right. So in terms of mean density, it will be soliton plus NFW profile. So it's going to be core plus NFW profile. And the quasi-particle here is fluctuation with respect to this mean density. Yeah. Yes. Yeah. Yeah. You are exactly right. So here I'm doing a little bit of use of the terminology. So this is not the particle in a sense that they are stable so that they are living long time over the scale of giga years. But this is really kind of a way to think about this structure. So this is not really kind of particle in a traditional sense, but yeah, I'm just using this because it will give us a useful tool when it comes to estimating how they interact with the stars, how they interact with the black holes or globular cluster and so on. So in that sense, this may be understood. Yeah. All right. So this is roughly the picture of quasi-particle. Again, there was some questions about this quasi-particle. The concept seems to be pretty naive, but there are many useful things that we can do with the quasi-particle picture without doing simulations or without going into complicated integral. So in order to demonstrate that, in order to see how we can understand this order one fluctuation in the wave dark matter halo, let me now discuss the particle dark matter halo. I mean, how we can understand this order one density fluctuation in the context of quasi-particle. So this is just usual particle dark matter halo. And if we zoom in the particle dark matter halo, let's say we fix the mass to be GeV scale. And if we zoom in close enough such that we are just talking about 1 centimeter cube box, and if we are asking the number of dark matter particle in this small box, there will be more or less order one particle because I'm fixing my dark matter mass to be GeV and I'm choosing the box size to be centimeter. The centimeter is the interparticle distance in this case. So in each of this box, there are order one numbers of dark matter particle. So there will be some boxes that will have one number of particle. Some boxes will have two, or some boxes will have 0 particles. And the number of these dark matter particle in each boxes, they will follow the Poisson statistics. So their mean value is given by this order one number. Their variance will also given by order one number. So if we are asking what's the density fluctuation over this small scale, over the scale of centimeter, even in the particle dark matter case, there will be order one density fluctuation because of this Poisson statistics. But if we are doing something like this, if we are increasing the box size such that the mean number of dark matter particle is like gigantic number, here I'm choosing a U scale box. And in this case, there is 10 to 39 number of dark matter particle. And because they are following Poisson statistics, now the density fluctuation over the scale of AU will be very, very small. So the density over here and density over here will be practically the same if it's a kind of dynamical equilibrium. In the case of wave dark matter, the order one fluctuation over the scale of wavelengths can be easily understood because we talked about the size of this quasi-particle can be astrophysical scale. So if we are choosing 10 to minus 15 eV scale, the size of this object will be AU. So if we are choosing the box size to be 1 AU scale, there are order of number 1 quasi-particles. So we are naturally expecting that there is order 1 density fluctuations over the scale of this wavelength. So this is very naive, maybe trivial statement to understand the order 1 density fluctuation in the case of wave dark matter. But there are other useful things that we can do with this quasi-particle picture. And the other useful thing is that, well, with this quasi-particle picture, we can easily understood the interaction between wave dark matter and the stellar object, or stars or black holes or other kinds of globular cluster and so on and so forth. So at most fundamental level, so there is a kind of quasi-particle just moving around in the simulation box. And because of the gravitational interaction, that will interact certainly with this kind of object, and they will bombard this test object, and they are sometimes dragging this object, or they are sometimes hitting this kind of object by injecting energy into the star's kinetic energy. So in order to understand the interaction between wave dark matter and the stellar object, at most fundamental level, we can just draw this kind of Feynman diagram. So I have this wave dark matter goes in and out, and there's some compact object. It can be a star, it can be something else. And because we are only talking about gravitational interaction, there is only one mediator, which is a G mu nu. So in the zero temperature QFT, in the zero density QFT, we can calculate the matrix elements. This is not working. Yeah, we can calculate the matrix elements in this way. So there's a Newton constant, there's a mass of this particle, there's a mass of this compact object, there's a momentum transfer like this. And under the Bohm approximation, we can translate that in terms of potential between these two objects. And this potential is usual gravitational potential, 1/r potential, where there's a mass of the dark matter particle and there's a mass of the star. So, but we're not talking about zero temperature, zero density QFT. So we are talking about a galaxy where there are tons of, oops, something is not. We are talking about the dark matter halo where there is a tons of dark matter already occupying the galaxy. So if we repeat this kind of calculation, what you're gonna see is that because the initial state and final state is highly occupied, there is an occupation number entering in the matrix elements and also in the potential term in this way. Again, this is a very naive picture, but if we remind the definition of effective mass, this effective mass is nothing but the product of this particle mass and occupation number, because the occupation number is density times the volume given by the wavelengths. So mass times this occupation number is going to give us an effective mass of this quasi-particle. Yeah. 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 Is it? Yeah, sorry. Maybe this is a typo, yeah. So maybe I was more thinking about the matrix element square. So I think you're right, because this is a T channel, so it has to be Q square in the matrix element level. Yeah, I think you're right. Yeah, I think so. Yeah. Thanks. So yeah, in this way, we can easily understand the interaction between wave dark matter with the stellar object by simply recycling this gravitational potential, but replacing the particle mass to the effective mass in this way. So again, this remains very heuristic. I mean, this all argument is a very heuristic argument, but we can, in principle, do more rigorous way. We can use kinetic equation like Boltzmann equation or Landau equation to show that this quasi-particle picture, the intuition coming from this simple picture, is more or less correct in many times. Whenever you try to calculate some diffusion coefficient, whenever you try to calculate some scattering cross-section, there is always additional occupation number factor. And we can always repackaging the expression in a way that you can recycle the classical expression, but with the quasi-particle mass instead of dark matter mass. So there are several interesting phenomenological implications of this wave-dark matter interaction to the star or black hole or other stellar object. So let me discuss some of them. So because of the interaction between dark matter and the stellar object, sometimes the dark matter kind of exerting a dragging force to the motion of the star. So here I'm assuming just usual particle dark matter. And here there is a homogeneous medium of dark matter. And I'm imagining that one star is moving in a certain direction. And because of a gravitational interaction, the dark matter particle, here the particle dark matter, they are attracted to the star, and there will be more density along this line, along the trajectory of the stars. And what does these over density do is that they are dragging the motion of the star, causing the orbit to decay. So what I mean by orbital decay, yes, was there a question? Yeah. So what I mean by orbital decay, so this is basically the frictional force, which is calculated by Chandrasekhar. And there are density and dark matter mass, stars mass, and there's a kind of Coulomb law, which is coming from the long range nature of the gravitational interaction. So what I mean by orbital decay, yeah. Yeah. So I mean here, let me spend 2 more slides, and then let's see this answers your question. Okay. Yeah. So here really we're talking about the scalar dark matter or wave dark matter, where they are interacting to the center matter only through the gravitational interaction. So in terms of action, I have an Einstein-Hilbert action and kinetic term and the mass term of this particle. So as long as the mass is within 10 to minus 20 to 10 eV scale, this picture will be more or less whole. But of course, the mass of the quasi-particle and the size of the quasi-particle will changes. Yeah. So what I mean by orbital decay is that even though we start with a completely circular orbit of stars around the galactic center or around the black hole, what does this dynamic reflection force does is that they are kind of dissipating the energy of the stellar object, causing the orbit to decay. So at some points, they lose energy and they are injecting energy to the dark matter medium, and they inspiral to the center of galactic center or into the central black hole. So one of the interesting things about this thing, this dynamic reflection, you can see it from the Fornax globular cluster. So this is a Fornax dwarf galaxy, and each of these circles are globular cluster. This is a cluster of the star. So by using this dynamic reflection, we can actually calculate what's the orbital time scale, orbital decay time scale of this globular cluster. And depending on their mass, depending on their radius from the center of this Fornax dwarf galaxy, you can calculate the decay time scale. And some of these objects, some of this globular cluster have a decay time scale less than 13 gigayears, less than 10 gigayears. So this is kind of causing some of the puzzle because, well, if the decay time scale is smaller than the age of this Fornax dwarf galaxy, why they are still orbiting far away from the center of this Fornax dwarf galaxy? So this is sometimes called Fornax globular cluster timing problem. And in the CDM, some of this globular cluster seems to be, having too small decay time scale to be explained their presence far away from the center of the system. So now I want to discuss how this picture changes in the case of wave dark matter. So we discussed that in the case of wave dark matter, using the quasi-particle picture, we can recycle the classical expression by changing the dark matter mass to the effective mass. And also here, because the quasi-particle, the size of the quasi-particle is so big, there is an additional modification in this Coulomb law. So the minimum impact parameter is now replaced by the size of this quasi-particle, so that there are some sort of suppression of this dynamic friction force. There's a softening, this is kind of softening scale. So if I redo the calculation here, I will see something like this. So in the case of fuzzy dark matter, in the case of ultralight dark matter, the decay time scale of each globular cluster becomes a little bit larger than that of classical cold dark matter, because their size is so puffy and they are suppressing the Coulomb law. There's a suppression of the dynamic friction force, and therefore their decay lifetime becomes a bit longer. So maybe this is kind of explaining this timing problem. So this is one of the interesting implications of wave dark matter interaction to a stellar object. So for here, the mass of dark matter particle is really close to 10 to minus 22 eV scale. So again, going back to your first question, this mass range may be in tension with astrophysical observation. So yeah, that's the status. Yeah. Yeah. So you mean in the Coulomb law, the logarithmic factor? Yeah, that's a great question. So in the CDM case, again, this is because of the long-range nature of this gravitational interaction. So you have to place a cutoff scale in terms of impact parameter. So there's a maximum impact parameter, there's a minimum impact parameter. The maximum impact parameter is naturally the size of the orbit or the size of the system, because beyond that, you don't have any matters to interact with. The minimum impact parameter is often decided by the size of the dark matter itself, or the minimum impact parameter where the approximation that is used to derive this expression breaks down, which is the, so here the assumption is they are doing weak encounter. So this encounter, through this encounter, the deflection of the particle angle is small. So this minimum impact parameter is often taken as the impact parameter where there is 90-degree deflection. So that's the maximum and minimum impact parameter for the particle dark matter. And for the wave dark matter, that is going to be, the maximum impact parameter will be the same, but the minimum impact parameter will be the size of these particles, the quasi-particles. So another interesting phenomenological implication is because of this interaction, the quasi-particle can inject the energy into the stellar population. So they are continuously bombarding the stars or black holes or globular cluster, and they are sometimes injecting the kinetic energy, and they are sometimes changing the orbital motion of these stars in an unpredictable way, in a stochastic way. So one of the consequences of that, those kind of interaction is that suppose that there is some sort of bound stellar object, like a cluster, star cluster. And if there's an interaction between wave dark matter and stars, and if somehow the parameters are chosen in a way that the wave dark matter is injecting the kinetic energy into the stellar population, what's going to happen is that the energy, the kinetic energy of the stellar population will increase, and this will result in an expansion of the size of the star cluster. So this is another interesting implications. And there are related studies in past 5 or 6 years where these people, David Marsh and Niemeyer, they looked at the star cluster in the Eridanus dwarf galaxy, and by estimating amount of the kinetic energy injected into the star cluster, and by comparing the size of the star cluster, they were able to constrain some part of mass range over this. And also, in some of the dwarf galaxies, the stellar kinematic data are pretty well known. So we know how many stars are there, and we know that how fast they are moving in some of these dwarf galaxies. So we can also study how much of the energy injection will there be in this kind of dwarf galaxy in the presence of wave dark matter. And we can also calculate the time evolution of this velocity dispersion. And by comparing the observation and the prediction from the wave dark matter halo, we can also constrain a certain mass range of ultralight dark matter. And another example is, again, similar to the first paper. They are looking at the star cluster in ultra-faint galaxies like a Cygru. And then they are doing numerical simulations of ultralight dark matter to see how the stellar population is reacting to the background wave dark matter, and comparing those numerical simulation with the observational results of the star cluster. They were also able to constrain certain mass range around 10⁻⁹ or 10⁻20 eV scale for the ultralight dark matter. So if there's a quasi-particle bombardment to the star cluster, the size of the star cluster will expand as a result of energy injections. So this is another interesting implications. So now what I want to do is that I want to discuss a little bit more about statistical property of this wave dark matter. So this may be a little boring, but there are many usage of this description. So I ask your patience. So now what I'm going to do is that I want to study the statistical property of this wave dark matter. So in order to study the statistical property of the wave dark matter, I want to start from just field theory. I have a classical scalar field, and I'm expanding my field in terms of creation and annihilation operator, A and A dagger, and there is a wave function over here. So what I have to do in order to specify the statistical property of the system, I have to solve for the wave function, and also I have to specify the density operator, because now we are talking about background dark matter. The wave function part is relatively simple. We can just solve a Klein-Gordon equation with the background gravitational potential. So in the non-relativistic limit, this is going to be kind of Schrödinger equations like this. So by solving this equation, we know the wave function of this system. Secondly, we have to specify the density operator of the system. So the density operator will be given by a direct product of density operator of each mode, like this one. And the density operator of each mode will be given by this kind of integral, where here P is a quasi-probability distribution, and here alpha is a coherent state. So the coherent state is something that when you act annihilation operator to the coherent state, they spit out complex number C. And once we specify the density operator and the wave function, by this trace operation, we can in principle calculate all the correlation function made out of the scalar field operator. If you think this is a little bit too complicated, there's a simpler treatment. So we can simply replace this creation annihilation operator to complex number alpha and alpha star, assuming that they are distributed over this probability distribution. We can just do the same thing. And because there's nothing quantum about this system, so we can really treat them as a classical random field. So to see its usefulness, how we can do what we can do with this kind of approach, let me choose one simple example where I am considering homogeneous medium. So yeah, okay. Okay, so yeah. Yeah. So here, yeah. Oops.
The assumption is what is the point of that because the current is the question is just how is you can replace it's okay. This is what we're out.
Yeah, yeah. So here, yeah, so here, okay, I mean, you can in principle do this trace operation, but because we are writing this in terms of Glover P representation, because we are expressing this in terms of coherent state. Any operation of annihilation operator to this state or creation operator will give rise to complex number alpha and alpha star. But when I do this approximation, when I replace the creation and annihilation operator to the complex number, of course, this is an approximation. There's a terms that I'm ignoring, but those terms are suppressed to some power, negative power of occupation numbers. So in the limit where I have huge occupation numbers, this approximation becomes incredibly good.
So I think the critical point is whether the system is solved.
Yeah. Yeah. So here I'm only assuming gravitational interaction. Here, so this approximation, I'm ignoring any interaction so far. So here, each mode is individual. They are statistically just different things. And that's why I just write it down as a direct product. And that's the thing. Here, I'm not assuming any interaction between these particles. Yeah. That's right. So there's a limitation of this approach, of course. The thing here is that I am assuming there's no interaction between particles. So whatever I do with this approach is valid to the time scale until you reach to the relaxation time scale, whichever you consider, right? Yeah. So that's my underlying assumption. And thank you for your question, because this is clarifying my underlying assumption. Yeah. So, okay, with that, let me just take the homogeneous medium. And in the homogeneous medium, my wave function is just plain wave. So what I want to do is that I want to draw this alpha from underlying probability distribution. And now I can kind of simulate the behaviors of this wave dorkmeter. So there are some of the order one density fluctuation just moving all around the box over the time scale of coherence time scale. And this is the same figure. So this z-axis is the density normalized with the mean density. And you can see that there are quite large number of density fluctuations going on in the small simulation box. And what is interesting is that you can see that factor 4, factor 5 over density is not that uncommon. This is happening all of this box, and this is a pretty common in this toy simulations. And we can also do much more than that, because now we have a statistical description of the system. We can in principle calculate all the correlation functions of density contrast or density operator or pressure operator, and so on and so on and so forth. So what I'm doing here is I'm calculating a 2-point function with a space-like separation. So the space-like separation, with the space-like separation, they are proportional to exponentials, which means that if the separation becomes larger than the wavelengths, the density fluctuation in these two patches, which is separated more than wavelengths, becomes uncorrelated. So the density fluctuation over here and the density fluctuation over here is completely uncorrelated. We can also study the temporal behavior. So now I want to look at the density contrast over here. So over the coherence time, their change is stochastic. They change their behavior in a stochastic manner. So for one coherence time, the density is like given by this value. And after the other coherence time, they change in a random way. So sometimes there is a more density in this box. Sometimes there's a less density in this box. There's a more feature to that, because if we look at very small time scale, there are actually some coherent oscillation at the frequency equal to 2m and the amplitude suppressed by v squared. So in order to understand this temporal behavior, the easiest way to think about it is just assuming that there is a single mode and we calculate the energy density, the density operator this way. So if I plug in the single mode, then there is a constant term, and this constant term is what representing the stochastic fluctuation in realistic dark matter halo. There are also terms that is suppressed by v squared, but oscillating at the frequency equal to 2m. And these oscillations, these terms is representing this coherent oscillation, which is suppressed by v squared. And these temporal behavior can be nicely packaged or described by spectrum of the density contrast. So we are calculating 2-point functions, and this 2-point function can be represented by frequency integral of power spectrum, density contrast power spectrum. And if we look at the density contrast power spectrum, there are two components in this system. One is a narrow peak at the omega equal to 2m, but their amplitude is suppressed by V squared. So this is what represents the coherent oscillation that we see on the at the frequency equal to 2m. And this broad low frequency spectrum is what characterized the quasi-particle behavior. This is what characterized the stochastic behavior of the density over the time scale of the coherence time scale, which is a 1/m sigma square. So this temporal behavior can nicely understood in terms of the spectrum. And what it can also do is we can now calculate the probability distribution of density fluctuation in one single patch. Really? Okay. I have to speed up. So, so the density fluctuation is given by the exponential profile here, exponential distribution. So we can easily calculate the probability of observing density much larger than pre-specified value, and they are proportional to this exponential factor. So with this probability, we can calculate what's the probability of observing a density contrast which is equal to 5, and that's more or less a 1%. But we see a lot of these factor 5 over density simply because there are many statistically independent patches. So that's why the density contrast which is equal to 4-5 is very common in this box. So another thing that we can do with this approach is we can think about how the wave dorkmeter is responding to a external gravitational potential. So one of the things that we can do is now we are imagining some of the star or sun at the center of the box. Now there's a gravitational potential. So because of this gravitational potential, the wave function will change in this way. So this is exactly the electrons wave function when their energy scale is larger than the binding energy. This is a free electron state where there's hypergeometric functions. So in this approach, we can also calculate the mean density over around the sun. So here I'm assuming that there are sun at the center of this box, and I'm assuming there's a monochromatic dorkmeter wave propagating from this direction to this direction. And because of this gravitational potential at the center of this box, there are more over density along the trajectory of the dorkmeter wind. There are little less density over here and here. And their pattern depends on the mass of this object. So this will lead to interesting signature, annual modulation signature, depending on their mass. So if we think about the particle mass such that the wavelength is much smaller than AU scale, the annual modulation pattern will be more or less similar to the particle dorkmeter. But whenever the wavelength becomes AU scale or larger than AU scale, the annual modulation pattern for the wave dorkmeter will deviate from particle dorkmeter. So there are maybe more annual modulation, or maybe there are less annual modulation if the wavelength is much larger than AU scale. There are also some deformation of spectral shape. So they are changing the velocity distribution because depending on the velocity, the way that they respond to external gravitational potential will changes. So if you have a smaller velocity particle, they are more actively interacting and responding to external gravitational potential. So there are enhanced power at the smaller frequency or smaller velocity. So I guess I don't have much time. So maybe I will just say a few words about another usage of this approach. So with this expansion here, what we did is we expand the scalar field. We specify the statistical property of this field. And also we determine the wave function in order to study the behavior of wave dorkmeter. So with this approach, we can actually construct a whole wave dorkmeter halo. So in order to explain how it works, let me first go back to the simulation result in terms of dorkmeter profile. So in many simulations, we have seen that there are smooth solitonic cores And outside of the solitonic core, this is given by something similar to NFW profile. So what we're gonna do is that we will make an ansatz. So we're gonna say that, okay, because of this numerical simulation, we know that the density profile will be given by a solitonic core plus NFW profile. So let's fix the density profile. And once we fix the density profile, we are basically fixing the gravitational potential. So once we fix the gravitational potential, now we can easily solve a Schrödinger equation. So we can solve the Schrödinger equation, and there will be a whole series of wave functions. And by doing this expansion again, we can also construct the whole wave dark matter halo. Here, we haven't decided the occupation number. So the way that we can determine the occupation number is calculating the mean density from this approach and comparing it to the target density profile that we impose as an ansatz. We can fix this kind of occupation number. So once we fix the wave function and occupation number, then we can completely simulate this, construct a whole wave dark matter halo. So this is the numerical result, semi-numerical result from this approach. So we can see similar patterns of this wave dark matter halo in this approach. There's a solitonic core, there's an order 1 density fluctuations. They are able to reproduce a soliton plus NFW profiles. And also they are able to reproduce a probability distribution of the density in each patches. We can also study their temporal behavior to see whether they matches to full numerical simulations. And we can also calculate the power spectrum of this wave dark matter halo with this handy statistical expansion. So how much time do I have? I can finish here. Okay, so let me say like real quick words about another application of this approach. So another applications of this expansion is that we can study adiabatic evolution of the system. So what I mean by adiabatic evolution is I want you to imagine this very simple picture. So here I have a uniform gas and I have a stars orbiting around the center. And because this gas participate in electromagnetic interaction, they lose energy. They scatter with each other, they lose energy by emitting photons. And this photon escape the system, so they are cooling down. And as they are cooling down, they adiabatically shrink to the center of the system. And whenever there's an adiabatic evolution of the Hamiltonian, what is well known in the classical mechanics is that your action variable has to be conserved. And one of the action variable here is the angular momentum. So in order to conserve angular momentum of the stars, we have to compensate the increase in enclosed mass with this orbital radius. So in order to conserve the angular momentum, the orbital radius of each orbit of the star has to shrink. So what's going to happen is that if there's an adiabatic shrink of this gas, the stellar orbit has to shrink in order to conserve the action, which is an angular momentum. And this is resulting in a steeper stellar distribution around the center of maybe central massive black hole, or this kind of adiabatically compressed system. And the same argument also goes for dark matter. Whenever there is adiabatic growth of the central black hole or a collapse of this molecular cloud in an early dark matter halo, the dark matter also should contract to respond to this adiabatic evolution of the system. And because of the adiabatic theorem that we all learned in the quantum mechanics course, whenever the Hamiltonian changes adiabatically slower than any characteristic frequency, they tend to stay in an instantaneous eigenstate, whereas their wave function follows smoothly to the instantaneous wave functions. So here in this picture, what I can say is that this occupation number will remain same because they remains in an instantaneous eigenstate. But this wave function will changes adiabatically to the response of the adiabatic change of the whole system. So if I just do this exercise for a hydrogen atom, so if I somehow can change the charge of the proton adiabatically, this is what's going to happen. This is a ground state solution. And as I'm increasing the proton charge adiabatically, so this is hypothetical situation, of course. But if I change the proton charge adiabatically, the wave function shrink towards the center and the density will increase. So this is what's going to happen also in the dark matter case. So in this hypothetical case with these parameters, if there is an adiabatic growth of the central black hole or some contraction of molecular cloud, then even though we start from this initial profile, there's a compression of the wave function such that they will result in steeper and denser dark matter profile around the center of the system. Of course, this is not the final picture because if there's a really black hole, these central soliton may be swallowed by those black holes. So sometimes the correct picture is not this kind of profile, but this kind of broken power law, because the central soliton and low angular momentum mode may have been absorbed by central black hole because they have wavelengths, they have non-negligible overlap with the black hole, so they are susceptible to be absorbed by central black hole. But even those cases, there are steeper dark matter profile and there are denser dark matter density around the center of the system. So in last 1 minute, I'm gonna say just few sentences about how we can test this compressed wave dark matter halo. So one of the ways to test this compressed wave dark matter halo is through the observation of gravitational wave. So what's going to happen in this adiabatic compressed halo is that whenever there's a compact object orbiting around the central black hole, what's going to happen is that they will lose energy by emitting gravitational wave. So they will lose energy and they will emit the gravitational wave. Their orbital radius will shrink. And as their orbital radius shrinks, the frequency of gravitational wave will increase. So this is the basic pictures. But because of the dynamical friction, because of the enhanced dark matter density, this orbit will decay much faster. There's a compressed wave dark matter halo. The dark matter density is much larger. And because of the dynamical friction, the orbit decays much faster, which means that the frequency of gravitational wave increase at much higher rate. So by comparing this waveform of the gravitational wave in certain astrophysical benchmarks, we can actually reconstruct the wave dark matter halo with this kind of parameters. So for the central black hole mass, which is roughly equal to 10 to 4 solar mass, and the companion object where its mass is around the solar mass scale, and whenever the mass of wave dark matter is around 10 to minus 13 eV scale, by just looking at the gravitational wave, we can tell the nature of this dark matter, compressed wave dark matters. And this is more or less all that I wanted to talk about. And thank you very much for your attention. Yeah, right. So here the parameter or astrophysical benchmark is we are thinking about dark matter halo formed very early, redshift equal to 20 or even higher. And there is adiabatic contraction of the molecular, I mean, this is a dark matter halo of mass 10 to 5 or 10 to 6 solar mass, so that you can actually form stars there. So, and then we are thinking of adiabatic compression of this molecular cloud such that there's a denser dark matter halo profile. And at the center, there are intermediate mass black hole. So we are considering those specific situations. We are considering if there's a compact object orbiting around the system, whether we can tell this is a wave dark matter or particle dark matter, or whether there's a no dark matter at all. Why we consider this one? Because one of the motivation for this kind of astrophysical benchmark is the presence of supermassive black hole at the high redshift. So we see from the quasar observation, there are supermassive black hole at high redshift, like redshift equal to 7 or 8. And one of the possible explanation for those supermassive black hole is to start from those intermediate mass black hole and start from there. So this is one of the motivation for this. Ah, yeah. No, here, yeah, here not we are not scanning the mass. So here we are choosing mass like different ways. So we are choosing 10 to minus 13 eV scale, 2 times 10 to minus 13 eV scale, and see, depending on the mass, how much we can reconstruct the wave dark matter profile. And why 10 to minus 13 eV scale? This is related to the frequency of the gravitational wave. So we are specifically thinking about LISA band. So this is a millihertz to say up to 1 hertz. And this 10 to minus 13 eV scale, the wavelengths of this object, the wave dark matter, is more or less similar to the radial distance of this compact object. So that's how this mass is chosen. That's how the system, the sensitivity of the system for the dark matter mass is determined. Yeah. So yeah. Yeah, so I think I should have included other figures. So we actually scan from 10 to minus 14 to 10 to something larger than 10 to minus 13 eV scale. So if you go to too small mass, then because of the larger wavelengths, the overall density will decrease because they have non-negligible overlap with the black hole. Black hole swallow all these things. So the signal will be weaker. If you go to very high mass, then now it's a little bit difficult to distinguish this from particle dark matter. So even though we see this kind of dephasing pattern, now we can ask whether this is a particle nature, whether it has a wave nature. It's a little bit difficult for higher mass. So 10 to minus 13 eV scale is the mass range where you can tell the difference of this wave dark matter from particle dark matter, and also have a non-negligible signal in terms of gravitational wave. Yeah, that's right. So there is a typical radius at which you can see the gravitational waves, and the wavelengths of this object, 10 to minus 13, is more or less similar to that. Yeah. Yeah, I'm aware. Yeah, I'm aware that there are discussions of the vortex, but I have to admit that I am not closely following those discussions, so I actually do not have your answer to your question. But that's an interesting topic. Yeah, certainly those things can happen statistically, and so when it comes to how we can see that, this I do not have answer to. Yeah, okay. Yeah, I mean, I'm happy to discuss, but yeah, that's interesting topics. Yeah.
I'm going to use Hyungjin when you discuss how to use the tool to speak before the symphonic before and then the end.
Yeah.
See, the starting point is to take the symphonic before and the SW.
Yeah. Right.
And so I think this how can you check it out? I assume that starting point.
So you mean in terms of construction of this whole dark matter halo with this expansion? That's an interesting question. So this is a kind of underlying assumption. So we are making assumption that we know the density profile of wave dark matter from this numerical simulations. And then by choosing this initial density profile, we calculate the wave function and also determine the statistical property. Once we accept this assumption, starting assumption, now what we can do is to calculate the statistical property and also kind of simulate the system to see whether they are actually matches to numerical simulation, full numerical simulation. So the way that I understand or digest this kind of approach is, again, this has to be compared with the numerical simulation. But once we are fairly sure about this density profile, if you take this approach, you can do other calculation much more efficiently, much more fast without doing full numerical simulation. So this is kind of two different approach. You gotta have to do this thing together But this way, you can calculate just by sitting down and analytically. This way, you do it from the first principle. So yeah.
But can you also what masses transfer and all that transfer what masses do they do the simulations?
So
First one was
yeah, so many of the simulations are simulating the structure where the structure is not hierarchically larger than the wavelengths. So if you are fixing the scale of this object to be galaxy sized, then many of the simulation can be interpreted as simulating 10 to minus 22 eV scale, 10 to minus 21 eV scale. If you go to much higher mass range, then this is numerically very challenging because now you have to much more grid. And I don't know whether there's a way to do that. So if I just want to simulate the galaxy size for the 10 to minus 10 eV scale, not sure whether we can do that with the current computers. Yeah. So many of the simulation is, if you fix the size of the system, that is going to be 10 to minus 21 EV scale, 10 to minus 22 EV scale. Yeah.
but the very like question related to the data.
Yeah.
If you start with your tool, the first line is prime, if you think of
Yeah.
then you set the mask for that, then minus
Yeah.
Starting with objects and see how that evolves.
That's very interesting question. I am not sure. I don't know. I don't know to your question. I don't have your answer to your question, but that's a very interesting question. Yeah, I'm not, yeah. I don't know. But let's discuss. I mean, that's an interesting question.
I mean, some masks can be higher than, let's say, 10 to the minus 1.
Related to this, the distribution of the carbon atoms. What you were showing is the basic.
Yeah, right. So you're asking whether, yeah, I mean, so that's where I'm kind of naive. So, well, yeah, you're right. So if I really calculate this distribution, the underlying probability distribution of the density for each patches, for sure, it's an exponential distribution. So what we discussed before that, it's kind of hand wavy, naive way to understand the order one density fluctuation. But for sure, the underlying distribution is exponential. Yeah, right. That's right. So I guess, I mean, again, going back to this quasi-particle picture, the way that I use the term is kind of naive because it's not really kind of particle in a traditional sense, in a sense that they are stable over a long time. So this is really kind of tool to understand many behaviors, but it's not, again, strictly speaking, particles. Yeah. So time scale of, very nice, very nice. I think for the low mass, if you go to 10 to minus 22 EV scale, even with gravitational interaction, the relaxation time scale will be order of giga-years or several giga-years. So after several giga-years, they will exchange energy, they will change the mode. They scatter and they go to the other state or go to the smaller state and so on. So I would say for 10 to minus 22 EV case, the time scale where this kind of approach is valid is few giga-years. But if you go to higher mass, then the relaxation time scale with the gravitational interaction will become much larger than 13 giga-years. And for that case, I think it can be valid for whole entire history of the universe. But now if you add another interaction, self-interaction, maybe this is a different story because it has a different relaxation time scale.
Somewhat related to this signature from changing gravitational waves.
Yeah.
Profile of the wave
Yeah.
near the center. How sensitive are the
cost, size of profile. If I introduce self interactions, and I also introduce viscosity, which is going to change the way the dark matter gets absorbed by the central black hole. And so that's definitely going to change further.
That's right. So that's a very interesting question. I don't know how to answer your question. But certainly they depends on the density profile. And because of that, here what we assumed is that the time scale, the relaxation time, I mean, here we are not assuming any self-interaction. We only assume gravitational interaction. And even with the gravitational wave interaction, again, the way that you can change the density profile is by scattering between the quasi-particles. So if the time scale of this system, the small dark matter halo, let's say its age is 10 giga-years, and if the relaxation time scale is smaller than 10 giga-years, that will certainly change this profile over the time scale of history of the universe. So in order to make sure that the density profile is intact over that time scale, we specifically ask this relaxation time scale to be longer than 10 giga-years. But of course, as you said, if you include self-interaction, they change the energy, and sometimes they push some of the modes to the low angular momentum or even solitonic mode. So there's a continuous dissipation of the density profile that will for sure change this capability of, let's say, LISA or search for this kind of compressed wave dark matter halo.
So the theory you were using, power, the dumbbells.
Yeah, here,
is the power.
yeah, here it's kind of broken power law. So
Yes.
yeah, so now the thing is that with the self-interaction or gravitational interaction, if there is a kind of relaxation, is this power law index going to be the same? And also, what's the maximum density? So this is a kind of open question, I would say, yeah.
So we thank you.
Thank you.